Now, last time we saw that for any vector space, we pick any vector space, you can find a set of vectors. From V. So in this V, you can find some vectors. Let's say this is that set, so that it spans V. So that it spans V. What does that mean? That means you can write any vector V from this vector space as a linear combination of these vectors. Not only that it spans V, but it also, these vectors are linearly independent. Which vectors? This set. Are linearly independent. So these kind of special vectors you can pick, which kind of generate the whole vector space for you and generate it in a minimal way because they are linearly independent. And that implies, we saw all these properties last time. So this kind of set, this set is called a basis for V. And one of the main properties we saw was that all bases for a vector space V have same number of elements. Same number of vectors. So like if we are considering the three-dimensional space, we call it three-dimension because any basis in it is going to have three vectors. Similarly, a plane is two-dimensional because you can think of it as a space of vectors and any basis of it. So like if I draw this plane, I can take these two as basis vector, I and j, and create all the other vectors out of these. Or I can take some others, this one and this one. But I will need at least two, and I can't have more than two, because if I have more than two, I can span the space, but those will not be linearly independent anymore. So the minimal set is two. So all bases for vector space have same number of vectors. So that number, therefore that number is called the dimension of the vector space. And then there were these very important facts. The very fact that it's a minimal set and all of them have same number of vectors, then you can prove different things, that how to pick this set. So any n linear, for an n-dimensional vector space, so all these facts are for an n-dimensional vector space. So with a vector space, this number is fixed, a dimension is fixed. Any n vectors that are linearly independent form a basis. So all you have to do is pick n linearly independent vectors and you are guaranteed that it would be a basis. Or you could pick any n vectors that span the vector space, they will form a basis. So you don't have to then check that if they are linearly independent or not, they will be. If they span, if they are n and they span the vector space, they will be a basis. If they are more than n and they span, then you know that they will not be linearly independent. So this fact, you can say any n plus k vectors that span V are linearly dependent. Well, you can even take this fact out, take this condition out. Any n plus k vectors will be linearly dependent. And since it's a minimal set, you also have this, that no n minus k vectors where k is bigger than 0 in both cases can span the vector space. So all these facts, this was the gist of last lecture. Now, these bases are not special. You can have infinite number of bases. You typically have, well, you always have an infinite number of bases in a vector space. But you can pick some very special bases depending on what you are doing. For this space, Rn, which we have been considering, which we were calling the space, the vector space of n column vectors. How did this come out? So for Rn, the vector space of n column vectors, we can choose a standard basis. So there's no fundamental importance to this standard basis, it's just a choice. It's a very natural one, very easy one, so we give it a name. A set of vectors which are a basis and a very particular basis, so we give it a name, a standard basis. So how does it look like? It has to have n vectors because we know that Rn is n dimensional. So first vector in this basis is just this. Second vector is this, and so on. The nth vector as a 1 over here. So in other words, that the ith element of this basis has 1 at the ith place, and all the other are 0. So you can very easily see that these are linearly independent and they span the space. So for example, if I consider, let's say, R4, and I pick any arbitrary A, B, C, D belonging to R4, you can very easily write, that's why it's natural. You just have to separate these numbers. It is this linear combination. or you can write it like this. So this would be the standard basis for R4. Now, you can similarly consider standard basis in other vector spaces, or you can pick any basis and call it that this is your desired basis in that vector space. Well, actually, there is not much structure in vector spaces. What is important is just the dimensionality. Once you declare the dimension of a vector space, if two vector spaces have same dimension, you can map one space to the other in a very natural way. And you can do it just by mapping the basis, matching the basis. So for example, let's consider this space. 2 by 2 matrices. We know that this is a vector space, and I can give a basis in this space. So let me write the basis. One basis for it. Now this is a basis because I can write any M belonging to this space, which would be of this form, as and you can also very easily show that they are linearly independent. We checked all this last time. Now the idea is that this is because it has 4 basis vectors in its basis. So this M2 by 2 is a 4-dimensional space. Now I have another 4-dimensional space. R4 is also 4-dimensional. So let me consider a map from this 2 by 2. So you have some map from this 2 by 2 to R4, and I define it using the basis. So I say that I have this basis element. So let me just map it to this guy. Or in other words, you're mapping M1 to E1. Similarly, I can map M2 to E2, M3 to E3, and so on. Now, once I have declared this, then any vector in M22, so if I have this guy, this is like a completely arbitrary vector. Since I can write it like this, so I just map it to this vector from R4. Yeah. R4 is not a matrix. R4 is a vector space. So this is the rule you have given, that I match the basis. I was given this, I knew that in my M2 by 2, I had 4 basis elements. I can pick R4 because R4 has also dimension 4. Its basis also has 4 elements. So then I match the basis in a particular order. Then I use this rule, linearity. This is called linearity. That this map was such that if I pick any element from M2 by 2, and I have these two, well, let's write it for any general vector space. If you have a map from a vector space V to W, it would be linear if I make a linear combination and apply the map to it, where V1, V2 are from this vector space V, it would be same as bringing the constants out and applying the map to the individual vectors. That's what I did over here in this map. I had these A, B, C, and D, and these vectors, M1, M2, M3, M4 are vectors because they are elements of the vector space. So I left these A, B, C, D out and applied the map to M1, M2, M3, and M4. And I knew that what does this map do to M1, M2, M3, and M4, which basis vector it takes it to in R4. So that means I can pick any element from M2 by 2 and map it to one specific element of V. Or if I'm given a specific element of V, I know which element of M2 by 2 is coming from. So this is a one-to-one mapping. So if you map the basis, so how to construct a one-to-one mapping? Pick a basis in your vector space V and map it to a particular basis in Rn. Now you will have to choose this n depending on what is the dimension of V. This n will depend on dimension of V because you have to match them. Otherwise you won't be able to do. You have to map one element to one element of the basis of Rn. And map it to a particular basis in Rn, then what you say, extend by linearity. If you expand a vector in V as, let's say, AI, and this is a basis of VI. VI, this is basis for V. You want to know where does this element go? This goes to this element of the Rn. So you have a one-to-one map. Or in other words, if you were given this element of Rn, because you know that EI match with VI, so you can go in the other direction as well. So that means all these vector spaces, they are same, kind of same. If I'm given any n-dimensional vector space, I can think of it as Rn. I can work with Rn. I can map it to Rn and think of it in terms of Rn, in terms of column vectors. So no matter what kind of vector space you are given, you can always convert it into space of column vectors and think in those terms. So let's take an example. So consider polynomials of degree 2. So these are all polynomials of this form, where A, B, and C are real numbers. And we know that this is a vector space. A basis for it, well, actually, this is a basis for it is x square, x, and 1. We have done all of this last time, and I have a feeling that people are lagging behind because I was looking at YouTube. Not many people have seen lecture 10 or 11, and many people have watched the last tutorial because I think people are trying to do the homework. And since there was an extension in the homework, people are just concentrating on those lectures. Because of this extension, I think people are starting to lag behind. So what I'm gonna do is give 2 homeworks with very close by due dates. And I tried to record a tutorial on Sunday, but was having internet problems, so couldn't do it. So I'm gonna post a tutorial tonight, and there will be a tutorial on Saturday, and I'll post a homework tonight which will be due sometime on Sunday, something like that, and another homework which will be due on Thursday next week, because I want people to catch up. Because of this extension and deadline, people have started to lag behind. So in any case, if you recall the last lectures, we discussed these things in detail. This is a vector space, and a basis for it is x square, x, and 1. You can very easily see that it spans any polynomial, and these are also linearly independent. Quick check. By definition, this is any polynomial, and I have written it as a linear combination of these vectors, which are also polynomials. And this is going to be 0. How can you make it 0? X and x squared, these are variables. They don't become 0. So this thing is going to be 0 only if and only if A, B, and C, you have to put all of them to 0. So that proves that they are linearly independent. And this checks that this is a basis. Now, what I'm going to do is map this basis. So it's a 3-dimensional space. So if I want to write them as column vectors, I have to pick R3, because that's also 3-dimensional. And I map, let's say, x squared to this guy, x to this guy, and 1 to this guy. So I just map this. Then any polynomial which is ax square plus bx plus c. For clarity, I'm going to write c as c dot 1. This is mapped to a x square is mapped to, so you use the linearity. A remains outside, x square is mapped to this guy, x is mapped to this one, and 1 is mapped to this fellow. So you get A, B, C. So instead of this polynomial, you can work with this vector, which is kind of natural because if you look at this polynomial, if you have an order in mind that I'm going to write, how is this polynomial defined? You just have to give 3 numbers. Because in this polynomial, what is there? X square, x, and 1 are fixed. You have some coefficients in front of x square, x, and 1. So you give me 3 numbers, the polynomial is fixed. So you can write those 3 numbers as well in a column and just keep in your back of your mind that the first number is the number corresponding to the coefficient of x square. Second is the coefficient of x, and third is the coefficient of 1. So if all you have to do is remember the order, and that order is fixed by when you declare this, that x square is mapped to 1, 0, 0, x is mapped to 0, 1, 0, and 1 is mapped to 0, 0, 1. So if you have this guy, this would be mapped to and so on. Now what you can do, because we also did this mapping, that was also kind of exactly same. I can map these column vectors to my geometric vectors. But this mapping is so natural that we call both spaces as Rn. So in this case, it's R3, 3-dimensional geometric space. So this was mapped to this I, unit vector pointing in the direction of x-axis. This was mapped to J, and this was mapped to K. Where J is the unit vector pointing in the y-axis direction, and K is the one pointing along the z-axis. Now we know that any vector over here we can write as a linear combination of I, J, K using head-to-tail rule. But any vector over here can be written also as a linear combination of these EI. So these are mapped to these. So I can map the polynomials to column vectors and then map the column vectors to these geometric vectors. So you can very well think of these polynomials in terms of this geometric space. So that's the whole idea. That's the advantage of thinking in terms of vectors. You're dealing with polynomials, but you think of them as some vectors pointing along some direction in a geometric space. So this guy is mapped to this vector, which is some vector over here. 3 in this direction, 2 in y direction, and 5 along the z direction. So something like that. I can't really draw a 3-dimensional picture. Something like that. So I think this is worth repeating, that all n-dimensional spaces When I say space, for our course, space is always a vector space. All n-dimensional vector spaces are identical in some sense, are kind of same. They can all be mapped to Rn. In the fancy mathematics language, people call it R isomorphic to Rn. But isomorphic just means that they can be mapped to Rn in a one-to-one manner. So any vector of any kind can be written in terms of column vectors. Any vector of any kind can be written in terms of column vectors. So column vectors become a prototypical example of a vector. People, and you will also, with some practice as we go along in the course, will start using them interchangeably. You're thinking of a vector, you think of a column. Or if you think of a column, you can relate it to some more abstract form of a vector. The best way to think about vectors is in terms of geometry, that this is some abstract space which exists in which you have vectors, but you can map all of them to Rn. Now, this idea that you can map the vectors spaces into each other can be, well, let me do it in another way. So let's consider, let me write what I'm going to do, but it will be clear as I do that what I mean by this. So if you, let's consider this space R2. So its elements are column vectors of this type. But all of these guys I can write as a linear combination of these two fixed vectors, which we called E1 and E2. So remember, in the beginning of the course, we settled on this notation that the column vectors, we're going to denote them with an arrow on top. But you might have noticed that when I was writing vectors from a vector space, I was also using this arrow symbol. So I'll use it for both. Whenever I have an element of a vector space, which we call a vector, it will have an arrow on top. But column vectors specifically, they also have an arrow on top. And those two things are interrelated because of this map as well. Because I can map these guys, any vectors, to column vectors. But sometimes it's helpful to remember that in this particular instant, you are talking about a column vector or an abstract vector. So that will be clear from the context. Just putting a vector will not always clarify if I'm talking about a column vector or I'm talking about an abstract vector from some other kind of space. So in this case, this E1 arrow is this particular column vector. Similarly, this E2 arrow is this particular column vector. And these two guys make a basis for R2. But this gives me an idea. This means that although this was the definition of this vector, but these components of vector A, B, which are A and B, can be thought of as what you call, some people call it components again, But just to make a distinction, I'm going to call, I think that's what the book does as well, can be thought of as coordinates of this vector AB in this basis. So AB were the components. That's how this vector was defined. But I know that any vector, I can expand it. I can write it as a linear combination of basis vectors. I picked the standard basis, and in the standard basis, the coefficients which come in front of the basis vectors are just these components in this standard basis. But we can expand the same vector the same vector AB in another basis. So suppose I pick these guys. Now there are two, I know I'm in a two-dimensional space. So for them to be form a basis, all I have to check is if they're linearly independent or not. So you can easily check. So the question is, do they form a basis? And you want this to be zero vector. If this happens, if and only if A and B are zero, then that would mean that they are linearly independent. But you get A plus B, A minus B on the left hand side equal to 0, 0. But this equation implies because equality means that the components match. A minus B is 0. This implies A is equal to B. Then this top equation implies A plus A is 0. That means A is 0, but A is equal to B. That implies B is 0. So this equation will hold only if both A and B are 0. Hence, these guys are linearly independent and therefore form a basis. Remember, if the number matches with the dimension, I have to check only linear independence. They will automatically span. So I'm now trying to find the coordinates or components in this basis. Sometimes people call coordinates in this basis, sometimes they call components in this basis. So I have to find these constants so that I make up this AB. So you get so I have to solve these equations. C plus D is equal to A and C minus D is equal to B. Very easy to solve. You add them. That gives you 2C is equal to A plus B. So that means C is equal to A plus B over 2. And if you subtract them, it gives you D equals to A minus B over 2. So these are the constants for it, the coefficients in this expansion. So C and D are the coordinates of AB in this new basis. So you can, just like this vector could be specified by telling A and B, and A and B turned out to be the coefficients in the expansion in the standard basis. Similarly, I can completely fix this vector because C and AB was arbitrary. Given any AB, I can find some C and D, which will describe the same vector. So I can collect this like this. And these two numbers fix the vector completely as well. Because if I know C and D, if I know these numbers, I can find what is A and B. So I can very well describe the vector using these two numbers instead of the original ones. So you then start thinking of these guys, that this AB as not, we started with giving this particular definition of a column vector. You collect these two numbers, but then we think of it as an expansion in the standard basis. So this same guy could be this, will be presented like this in new basis. So you call it representation in the new basis. So the same vector in one basis looks like a different column, and that very same vector in another basis will look like another column, depending on what basis you are using. So there's a slight chance of confusion because that's how we started. We didn't start with an abstract definition of vector space. We started with the definition in terms of two numbers, x, y. And we said that this is a fixed vector. Let's call it V. Now I turn around and I think that this vector V is some abstract entity. It would be very helpful if we think in terms of geometry. So X units here and Y units here. It is this kind of abstract entity in some abstract vector space. You can always imagine it to be the abstract geometric space. Its components are x, y. So it looks like these two numbers. When I expand it in terms of these I and j, which are also these guys. But the vector exists independent of these I and j. It's just this directed line. I could very well expand it in terms of these guys. And these guys, how do they look in the geometry? This guy, if I call it U1 and call it U2. So one in this direction, one in that direction. So it's a vector at 45 degree over here. And this is U1. And U2 is a vector, one going up and one going to the negative x. So it's at 45 degree in this direction. So I could very well construct my V in terms of this U1 and U2. V exists in itself. When you look at it in terms of I and j, it gave you these numbers, x, y, which were its components in this ij basis. But I can write it as a linear combination of U1, U2 basis as well. Then it will give me some other number, some other coefficients in front of U and U2, so that when I add those parts of U1 and U2, I construct V. Those I can collect over here and call it some new components in this new basis. For these particular bases, I found out that this is the relation. If in the first basis you had a, b, in the new basis you had a plus b over 2, a minus b over 2. Let's take another example. Again, you have I and j, which is your standard basis. And now I consider a new basis. Uh, Now, the order of how you write the basis elements also matters, because what you are doing over here, when I had the standard basis 1 0 0 1, and I take a vector a b, wrote it as a linear combination like that, or maybe if I take a vector over here ai plus bj, and if I'm writing it as AB, A is the coefficient of the first basis vector, and B is the coefficient of the second basis vector. So I need to know that which one comes on top, which one comes at the bottom. So the ordering, you just imagine an ordering. You just give, when you specify a basis, you also give an ordering in order to represent its expansion as a column. Because if I take, so let's consider some arbitrary vector space. Let's say it's three-dimensional vector space V, and you are given a basis. Any vector V over here can be written like that. This is all you need. You don't need any ordering at this point. But now suppose you know that this is completely specified by giving the coefficients of these basis vectors, because any vector V can be written like that. If you give me the coefficients of V1, V2 and V3, you know what vector you are talking about. So I want to collect these numbers in a column. But in a column, I have some ordering. So I need to know that at the first place, which coefficient is going in. So at this point, I imagine an ordering in my mind. So I say that the first basis vector is V1 and its coefficient is coming first. Second basis vector is V2 and its coefficient is coming next, and so on. So like if I have this vector AB, and this is my standard basis with this particular ordering. If I change the ordering, if I say this is my basis, same vectors, and expansion would be still same. So now I say that I want to write this guy as it would still be same. But since you have now given this ordering, you are saying that first I'm going to put the coefficient of this guy. And then I'm going to put the coefficient of the second basis element. So I write it like that. So by reversing the ordering, the way you write the column vector would be reversed. So this is representation in the standard basis. When you say standard basis, it comes with the standard ordering. with standard ordering. This is representation in the reversed ordering. So you have changed the ordering, you have kind of changed the representation. Now I was doing, this remark was very important. It came into my mind because I was trying to take this basis and trying to write AB in terms of this basis. First of all, how does it look geometrically, this basis? So the first element, if I call it U1, I call it U2, is just the J vector. The vector pointing in the x direction, in the y direction. The second vector is just the minus I vector. So that means I reversed. So you are dealing with this basis, which is totally fine. And how can I write? I have to construct a B here. So I put a B in front of this guy. And I have to construct an A here. For that, I will need a minus A. So with this basis and this ordering, AB is written like in new basis. B minus A. Now you can very well imagine that this guy, I'm saying this is the first, this is the second. Originally I had, this is the first, this is the second. I replaced this basis with this one. In this one I had AB, in this one I had B minus A. But if you think in terms of an abstract vector, like something living geometrically in the plane, which basis is better? Well, this is just an orientation. Like if you choose this one, someone could be, and you're standing here, you call it that this is X. If I rotate it, it becomes this. So someone else, if you are sitting like this, standing like this, you would be probably calling this as X, this as your first vector, and this as Y. So in a sense, there is not any fundamental importance, as I said before, in I and J. It's just a choice. And this guy wouldn't even know that you call this as the standard basis. So they will work with this and they will start constructing their columns. So there's no fundamental preference in between these two columns. You have to specify which basis you are working with. This became for us more important because we had given the definition in terms of two numbers. But thinking abstractly, both are on equal footing. You have to specify which basis you are talking about, and then you have a particular column associated with it. So, any question? Now let's see if we are given, we have done this example, if you are given the components in one basis of a vector, how to transform them into components in another basis. but I just want to discuss, we did it explicitly. How does it work out in general? If you're going from any basis to any other, we took specific examples of going from one basis to another. How does it work out in general? So let's consider, I'm again going to construct it first by doing another example. So suppose you are given this, let's say 1 minus 2. And you want to find out that if you are given these components, in the standard basis, how to find components in U1, U2. In other words, these C, D, which are these guys. You want to find out CD such that C U1 plus D U2 constructs your original vector AB. Or you can reverse it as well if you know the components in U1, U2 basis. So that means, and they are CD. So that means how to find the components in the standard basis. So you have this general vector V, and you are writing it as C U1 plus C U2, and you want to see how I can write it in terms of, so I'm first answering this question. So you are given the expansion of this V in terms of U1 and U2. And this turns out to be CD. So these two numbers, CD, representation in this new basis is given. And you want to find AB representation in this basis. So it's very useful to write it as an abstract vector V. So all you are saying is that the CG, these two numbers come up because this V is a linear combination of U1 and U2. But now here comes a technique which we will be using again and again. That I know that E1, E2 is a basis. So that means even this basis vectors, they can be written as a linear combination of E1 and E2. So let me write U1 is this guy. So how will I write it? because it's the standard basis. So these numbers are just the coefficients in terms of in front of the standard basis vectors. And what is U2? We chose it to be 1 minus 2. So these numbers, I know I don't have to do any work. Since this is the standard basis, these numbers are just coefficients. In the standard basis. So now I can replace these guys over here. And then I get, how do I? So if I do this V can be written as E1 plus 1 times E2 plus D1 times E1 minus 2 E2. So now I want to write the components of V. So I should collect the numbers in front of E. E1 plus C times 1 minus D times . So these are those coefficients which I was after. So A is C times 1 plus D times 1 and B is C times 1 plus D times minus 2. Now you can see that I can write it as a matrix equation. Because I know the rules of matrix multiplication. So this is just this thing. Right? When I'll do the matrix multiplication, I'll get this first equation, A is equal to C times 1 plus D times 1, B is equal to C times 1 minus 2 times D. So here is representation in U1, U2 basis, while here is representation in the standard basis. And they are connected. These two representations are connected through this matrix. And what is this matrix? If you look back, this is just a matrix constructed from U1 and U2. Right over here. U1 was 1, 1 and U2 was 1 minus 2. So in other words, what we have discovered is that this AB, this representation in standard basis, you come to it from representation in U1, U2 basis by multiplying with this vector, with this matrix. Where U1, U2 are the vectors, are the representations of U1 and U2 in the standard basis. And actually, I can also write this equation. U1 and U2, since they were linear combinations of the standard basis elements, so U1 was 1, 1. and u2 was 1 minus 2. Because if I'll open this up, this is same equation as this one. This is 1, and I have written this also. This is 1 written in a matrix form. Although each component over here itself is a matrix, I'm just writing a linear combination in terms of this matrix. Well, u1 was 1, 1, u2 was 1 minus 2. Yeah. And this matrix is just you construct by writing the representations of u1 and u2. So let's see how does this work in general. So in general, if I am given a vector v, it will have its representation in terms of the standard basis, where now I goes from 1 to n. Any, for now we are working in Rn, n-dimensional space. Then I consider another basis. Ui is also a basis. But this ui will be, each element of ui can be written as a linear combination of my original basis elements, right? Because they are bases. They span the whole vector space. So even these basis vector, new basis vectors can be written as a linear combination of the old ones. But I'm over here picking the ith. For ith, I will have specific numbers. So to specify that, I put an I over here. There's a sum over j, but I is fixed for a fixed I on the left hand side. For each vector from the basis set, I'll have different numbers over here. Now, if I write V, I will have, I can expand it in this new basis. But now I can replace this thing. So I have So if you look at this equation, what is it telling you? You're expanding V. You started with expanding V in terms of the U basis. But now you have written it as an expansion in the E basis. You call it J, I, doesn't matter. It's just an index. And these are the coefficients of this V. So that means these are CIs. These are the expansion coefficients of V in terms of the original basis. So these are the CIs. So CI, not CI, J's. There's an index J over here. So these are CJs. Doesn't matter you call them J or I. So jth C you get by doing this. So jth C, I can also write it as, I want to write it as a matrix multiplication. So I can replace this by the transpose. Now what is it telling me? It's telling me this is the rule of multiplying a matrix with a column. So this is telling me that if you want to construct the column which represents your vector in the original basis, in terms, you can do it by writing the column which represents the matrix in U basis and multiplying it with this A transpose matrix. What is this A transpose matrix? Let's look at this guy. What is A transpose? Or what is A? If you know A, you know A transpose. So if I fix, let's say U2, I am having these numbers. So I am having A21, E1 plus A22, E2, so on until you have this thing. That means if I collect these guys, this will be the column representing U2 in this E basis. It will be just exactly the column of U, how you write U in terms of the E basis. But the first number, we usually call it row, and the second number, we call it column. While here, I'm fixing this 2 and going over 1, 2, 3, 4. The second is supposed to be column, but it's varying with the rows over here. So this, the way I write it, it becomes a row. If I want to write it as a column, I have to reverse the role of rows and column. So if I collect this thing, each row is giving the components of UI in E basis. Each row. So if I take the transpose, then each column constructs the components of rows are replaced by columns. Each column gives me the components of UI in the EI basis. And that's what I'm doing over here. That means you can get this C by this matrix U, where U is just this matrix. Constructed with the columns of the new basis. So we are running over time. Let me stop here because I think this is a little difficult part. We will have to go over it slightly again, and then I'll do some examples of it, so it will become clear next time. Any questions? Let me again warn you, if you will, the first part was kind of very slow. We will pick up some speed, and if you do not work regularly along with the lectures. If you fall behind, you won't get what's happening in the new lecture. Well, you can always catch up. I think that's what most people are doing. They're watching the lectures sequentially, but they haven't caught up with the latest ones. But it will just become too much at the end.